All right, let's dive into one of the coolest ideas in all of chemistry, equilibrium. Now, when you hear that word, you might think of something that's just stopped, a reaction that's run its course. But that's not it at all, not even close. Chemical equilibrium is actually a super dynamic, high-energy balancing act that's happening constantly all around us. Think about it. It's happening in giant industrial factories and even inside the cells of your own body. So what does this balancing act really look like when you get down to the molecules? Let's find out. So, here's the game plan. We're going to start with the absolute core concept. What is dynamic equilibrium? Then, we'll figure out how to put a number on it with the equilibrium constant. After that, we'll explore how we can actually poke and prod at a reaction to shift the balance, using something called Le Chatelier's principle. We'll also see why temperature is the one variable that gets its own special section, work through a classic calculation, and then tie it all together with a massive real-world industrial process. Okay, let's get right into the big idea. We're talking about reversible reactions here. You know, the ones that can go forwards and backwards. But what does it actually mean when a reaction like this finally finds its balance? Think about it for a second. If you have reactants turning into products, but at the very same time, products are breaking back down into reactants, when do you call it? When do you say, okay, we're at equilibrium? Is it just when you have the same amount of stuff on both sides? Well, not quite. Here's the secret. It has nothing to do with the amounts being equal. It's all about the speed, the rate of the reactions. We hit dynamic equilibrium at that perfect moment when the forward reaction, reactants becoming products, is happening at the exact same speed as the backward reaction. It's a state of perfect, continuous motion. Right. This is a super common mistake people make. Because if you were to just look at a beaker that's at equilibrium, everything looks static. The color isn't changing, the pressure's stable. It looks like nothing is happening. So did everything just grind to a halt? Absolutely not. If you could shrink down to the molecular level, it would look like total chaos. Molecules are constantly colliding, forming products, and at that very same moment, other product molecules are breaking apart and turning back into reactants. The key is that both of these things are happening at the exact same rate. So even though there's a ton of action, the overall amounts we can see and measure don't change. Now, for this whole balancing act to even happen, there are a few ground rules. First, it has to be in a closed system. You can't have stuff escaping or being added from the outside. That way, the reaction is the only thing in control. Second, all the big picture properties, the things you can actually measure, like concentration or pressure, they all become constant. And finally, you'll always end up at the same equilibrium point, no matter which side you start from, all reactants or all products. That balance point is just a fundamental property of the reaction itself. Okay, so we've got the concept down. But you know chemistry, we love to put a number on things. How can we actually quantify where that balance lies? Does it favor the products or does it favor the reactants? Well, that's where the equilibrium constant comes in. We need one single value, a number that can tell us everything we need to know about the balance point for a specific reaction at a specific temperature. A number that perfectly describes the relationship between how many products and reactants you have once everything settles down. And this is it, the equilibrium constant, which we call Kc. The setup is always the same. You put the concentration of the products on top and the concentration of the reactants on the bottom. And here's the really important part. You have to raise each concentration to the power of its number from the balanced equation. So if you get a big Kc value, that means the top of the fraction is bigger, you've got more products. If you get a tiny Kc value, the bottom is bigger, and the balance favors the reactants. Simple as that. And just so you know, Kc has a cousin named Kp. It works the exact same way products over reactants. The only difference is, instead of using concentrations, which we do for reactions in a solution, Kp uses the partial pressures of gases. So if you're dealing with a bunch of gases, Kp is your go-to. Same idea, just a different way of measuring the amount of stuff. Okay, so we've got our system in a nice, happy balance. But what happens if we mess with it? What if we change the conditions? This is where this really cool, really predictive idea called Le Chatelier's principle comes in. Think of it like this. The equilibrium system wants to stay balanced. So if you come along and apply some kind of stress, like you change your concentration or the pressure or the temperature, the system is going to fight back. It will literally shift its position to oppose whatever you just did, trying to get back to a new state of equilibrium. Let's run through a few examples. Say you add a bunch more reactant. How does the system fight back? It shifts to the right, towards the products, to use up what you just added. What if you crank up the pressure on a gas reaction? The system will shift to whichever side has fewer moles of gas to try and relieve that pressure. And what about temperature? For an exothermal reaction that gives off heat, heat is like a product. So if you add more heat by raising the temperature, the system shifts left to try and absorb that extra heat. It's incredibly predictable. All right, let's zoom in on temperature for a minute because it's special. When you mess with concentration or pressure, you're just shifting the position of the equilibrium. You're not actually changing the fundamental balance point, the value of Kc. Temperature, though, temperature is the only thing that can actually change the value of Kc itself. Yeah, let's be super clear on this. When you change the temperature, you're not just giving the balance a temporary nudge. You are fundamentally redefining where that balance point is. The value of Kc is completely 100% dependent on the temperature. So here's how it works. For an exothermic reaction, one that releases heat, jacking up the temperature makes the forward reaction less favorable. The equilibrium shifts left, back towards the reactants, and so the value of Kc actually gets smaller. But for an endothermic reaction, one that absorbs heat, raising the temperature is like giving it exactly what it wants. The equilibrium shifts right, making more products, and the value of Kc gets larger. All right, enough theory. Let's put this stuff into practice. A really common thing you'll need to do is calculate the value of Kc using some lab data. So let's walk through an example together. Okay, here's our setup. We start with a certain amount of N2O4 gas, which can decompose into NO2 gas. We know how much we started with, and we know how much of the reactant is left over once the system reaches equilibrium. The mission is to find the value of Kc. The absolute best way to tackle this is with a tool called an ICE table. That stands for Initial, Change, and Equilibrium. So initially, we have 2.0 moles of our reactant and 0 product. The problem tells us that at equilibrium, we have 0.8 moles of the reactant left. So the change is pretty simple. We lost 1.2 moles. Now for the magic part, we use the stoichiometry. The balanced equation says for every 1 mole of N2O4 that reacts, we form 2 moles of NO2. So if we lost 1.2 moles of reactant, we must have gained 2 times that, or 2.4 moles of product. Now we just do the math and we have our equilibrium amounts for everything, 0.8 moles of reactant and 2.4 moles of product. Now for the easy part, we just calculate Kc. First we write the expression. It's the concentration of our product, NO2, squared, divided by the concentration of our reactant, N2O4. Now, since the container volume is 1 decimeters cubed, the number of moles is the same as the concentration, which is handy. So we plug in our equilibrium values from the ICE table, 2.4 squared on top, divided by 0.8 on the bottom. That works out to 5.76 divided by 0.8, which gives us a final answer for Kc of 7.2. Okay, so why do we care about any of this in the real world? Well, let's look at maybe one of the single most important chemical processes in human history, the Haber process. This is how we make ammonia, which is the key ingredient in fertilizers that help feed literally billions of people. The reaction to make ammonia gives off heat. It's exothermic. Now, Le Chatelier's principle tells us that to get a high yield, we should use a low temperature. But here's the catch. At low temperatures, the reaction is painfully slow. A high temperature makes it go fast, but gives you a terrible yield. So what do? Industrial chemists found a compromise, a sweet spot, right around 450 degrees Celsius. They also use incredibly high pressure, about 200 times normal atmospheric pressure, because that shoves the equilibrium to the right, the side with fewer gas molecules, boosting the yield. And to top it all off, they throw in an iron catalyst just to speed things up without changing the equilibrium itself. It is a masterclass in using these principles to make a process economically viable. And that really is the heart of it. The biggest thing to remember from all of this is that chemical equilibrium is not a dead end. It's not static. It is a constant, dynamic dance between forward and backward reactions. It's this incredible, perfect balance in perpetual motion that chemists have learned to understand, predict, and even control to literally shape the world that we live in.